In a world where space and time are intertwined, one man dared to challenge the status quo. His name? Dayton Miller. His weapon of choice, a flute. But not just any flute. This instrument held the power to unleash the ether, a pervasive medium once thought to fill the universe. Miller, a physicist by trade, a musician at heart, discovered a harmonic resonance within the ether. He found that his flute, when played with precision, could manipulate this elusive medium. His melodies, a symphony of science, had the potential to shift the very fabric of reality. However, a sinister force lurked in the shadows. The Einsteinian demons. These creatures thrived in the distortion of space-time, causing chaos and disruption. The world needed a hero, and Miller was ready to answer the call. With his flute in hand, Miller played a tune that echoed through the cosmos. Each note, a shot of pure ether, struck the Einsteinian demons, dispelling them back into the void. The world was saved, not by a warrior, but by a musician, a scientist, a man with a flute. Remember, in this universe of wonder and mystery, sometimes the most unlikely heroes make the biggest impact. Keep your mind open, your heart brave, and who knows, you might just find the ether within yourself. So here's to Dayton Miller, the flute ether.
All right, gentlemen, we're live. Thank you, sir. Give me 1 second. I'm going to restart Discord. My virtual webcam didn't seem to pull through. Dang, that sucks. I was going to do it from that so you guys could see me as well. Why is that wrong color? 1 second. There we go. I know that made it worse. 1 second. Is that it? No. There we go. All right. Well, all right. No worries. No webcam. Sorry about that, lads. All right. Here is the presentation, though. All right, we're live. All right, the color is off. Hang on 1 second. My webcam turned me yellow. Just need to see if I can fix that. No. Well. Nope. Yeah, it's definitely not the right color. All right. It doesn't matter. All right. Relativity of Simultaneity and the Sagnac Effect, an Aether Cosmology presentation by SpaceAudits. So this is something we talk about a lot here, the Sagnac Effect, and we're often faced with dealing with relativity because that is the current mainstream paradigm, right? The current mainstream physics is built upon special relativity, general relativity, and quantum electrodynamics. So what we're, as we're coming to our own with Aether Cosmology, what we're having to battle with is going through the history of physics and reinterpreting, experiments and figuring out what the Aether interpretation of that would be, without covering it up or without doing convoluted math equations to, make the measurements whatever we want them to be, just trying to take them at face value. So this will be a presentation focused largely on the Sagnac effect and its impact in physics, because it's like one of the most impactful things, and they don't, it's obfuscated through the lens of relativity. So we're going to go extreme into the history of that. Okay. All right. All right. So to begin, kinematics and dynamics, to quote from Bennett the other night, if you remember nothing from this presentation, kinematics is measurements, dynamics is predictions of motion. Here are the equations that dictate kinematics. And equation number 3 is missing a t squared at the end there. It's a error in the display for whatever this is, Obsidian's preview thing. Anyway, so what they describe is change in distance over time and acceleration, things like that. You can use these equations to figure that out. There's no causal mechanism involved in why the motion is happening, but it's just predictions of motion based off of changes over time, right? And then when you get into, there should be a dynamics slide to follow that up. Okay, so anyway, the dynamics is the future predictions based off of real forces. So the slide for that's missing. I apologize. Back to, dang it. Hang on. Trying it from a new interface here. Okay, so the important equation here that will be, or the important reference that will be talked about a lot is c, light, the speed of light. The way that it was derived, right, was from a rate of induction of nu equals the reciprocal of epsilon times nu, or mu, which is the magnetic permeability and electric permittivity in a vacuum, and that induction rate equals approximately 300 million oscillations per second. And they use that as that induction rate for the speed of light. So when they talk about how fast light can travel, it's in that they've equated that oscillation rate to a distance over time, and through that metric, that's the speed of light, right? Man. Okay. All right. Now, when Maxwell's equations were derived, and there were some subsequent experiments that went on, and we're told this narrative that only special relativity could rectify Galilean relativity with electrodynamics, and this is done by introducing the time variable, right? So special relativity introduces the t variable to the XYZ Cartesian coordinate system, and making it, adding that fourth dimension, they say, right? So with that fourth dimension, they're able to describe motion, right? Because what's motion? It's a change over time. Well, you can't describe motion if you don't have the metric to to have it based against, right? So the introduction to time through special relativity, we're told, is like this mutually exclusive. We were lost in the dark. Can't figure out nothing without the introduction here. Well, the way special relativity talks about time, right, is it breaks it down into proper time and coordinate time, where proper time would be the time in the frame of motion, and the coordinate time is set to the rest frame, right? So if there's two observers in relative motion, one of them will be in rest, and that will be the coordinate time, and the one that's in motion will be the proper time, right? And he will measure everything at the speed of light. If he's in rectilinear uniform translatory motion, then he'll measure the speed of light at c, because he'll experience link contraction proportional, right? But to his velocity. But let's see here. But anyway, what the point here is to make it seem like time is in the moving frame, and it's arbitrary in setting the coordinate time to, like, literally calling the rest frame coordinate time as if it's just like as if that's just some arbitrary ds. And proper time is defined by the moving frame, because everything's relative, right? So that's the distinction they made there. But there was already a derivation for it by Hertz and some other people, and you can actually use this. It makes all the same predictions, right? So instead of you having time as partials, you have it as an absolute, and then you have the motion frame, right, as the differential from the proper time. See, like that would be, you just invert it to coordinate time, and oh my God, everything works again. Nothing's broke. Everything's fine. Right? So it's just a little story that we're told about the mutual exclusivity that relativity brought to the table. You know, it's like we couldn't even do anything without that. I mean, Jesus, it's kind of the thing that they're put forward. So the experiments leading up to relativity, prior to relativity, were the physio drag and ergo and Airy's failure and the Michelson-Morley experiments, right? There was just consistent measurements of the Earth not giving that response where the velocity would be detected using optical media, in the way that they were coming to the understanding that you could use optical media to measure relative translatory motion, so anyway, so after 1887, Michelson-Morley, which we'll come back to after we get to what was put forward to rectify why these experiments produced a measurement that didn't correspond with the velocity component that would be required for the current heliocentric paradigm to be true, where they've based everything off of ratios of Kepler's laws and then applied Newton's equations to it for a dynamic explanation, meaning that the reason things move in the sky is the mechanism of mass attracting mass. And then when they tried to measure that, they could never do it because, you know, the implication is that we're stationary, and this theory was put forward to explain that. So we're going to go over the baseline of it, and then we're going to see if it's ever been experimental, if it's ever been true at all, and where, you know, and then we're also told today in current technology, nothing would work without the relativistic interpretation, blah blah blah, and we're going to see if current technology is dependent upon it. 1 second. So going to see if anyway, so because we're told that GPS explicitly wouldn't work without special and general relativity, not just one relativity, boys, the double relativity, right? Uno dos relativities. You need them both for GPS to work, they say. So this is On the Electrodynamics of Moving Bodies by Albert Einstein, 1905. He puts forward a conjecture based off of the experiments where they failed to detect the Earth's motion and the explaining the Lorentz force, that, you know, all motion is relative to something. And the conceptualization of electromagnetic propagation and lines of force and all that was, you know, through this medium, like a fluid medium, an all-encompassing medium, right? But their conceptualization of it was mostly stationary because they couldn't rectify it logically with experiments where they would get like a drift measurement, but then it wouldn't be a measurement that would correspond to heliocentrism. So they were really trying to narrow it down to this is the cause of they were trying to get that elusive first order measurement of the Copernican principle, dude. That's really what they were trying to do. So anyway, Einstein says here that in any frame where the laws of Newton hold true, right? So going back to Newton bucket, any frame where you don't have to introduce fictitious forces or the laws of dynamics make the wrong prediction, right? As long as they hold good, this theory will hold good. And further, he says that the speed of light is independent of the motion of the emitting body, right? And what he means to say here, because this is a little ambiguous, but he's not saying anything new by saying that, although physicist lads knew that at the time, right? That's not how wave propagation works and how it's measured. It's relative to you, like the speed that you measure a wave is relative to your velocity. So what he's meaning though is that when you're in the uniform transitory motion, that your motion can't be measured either, right? That's what he means to say by that. So when we're in relative motion with the sun, that's why we can't measure it, because we're link contracted, like that moving frame, that proper time, we're experiencing link contraction in that direction of motion. So we can't measure it. When Michelson turns his interferometer on, he says that the measurement that they got was close enough to a zero that they just said that they couldn't measure it, or, you know, that the speed of light was constant and there was no deviation. So based off of that logic, this is where they're taking it, right? And he says here that the introduction of a luminiferous ether, so an all-encompassing fluid medium, will be superfluous in so much here as the theory will not require an absolute stationary space provided with special properties, nor will it assign velocity vectors to a point of empty space in which electromagnetic propagation take place. So here he's removing the physical substance of it, right? And the mathematical construct of it, where it's the preferred frame that you would use to measure all motion relative to it. And he's saying that you can, with his theory, you can explain relative motion without invoking absolute space to accurately measure the relative motion. All right. Next slide. So in the kinematic part of the theory here, we call it the stationary system, and then he's going on to define time and proper time earlier. So earlier I kind of went into detail about it with the Hertz thing, but this is the introduction of the idea that there's no absolute time, there's no absolute space. When he says to a friend, locally, hey, meet me at 7 o'clock for coffee, that guy knows what 7 o'clock is. But somebody in another time zone would have no idea what 7 o'clock is. Like, it would be a different time, right? So it's relative, like this is what he's getting at. So, and then he goes on to define proper time as the time in the moving frame relative to the coordinate time, which is the irrelevant arbitrary frame that doesn't matter. All right. And then he goes on to show here a roundabout way to say that the one-way speed of light is equal to c, like from the way Maxwell derived it, with the reciprocal of epsilon and mu. So what he's showing here is that the time that the signal will take going back and forth will be equal, right? Is essentially what he's saying. And he does this through a nice little thought experiment in his dome piece. And that's about it. So he's establishing this, and then obviously this is in a vacuum, so we're not accounting for any media drag or anything like that. So, all right, there we go. So that's how he's establishing that one-way speed. Sometimes you'll hear people say, oh, we can't measure the one-way speed. We don't know the one-way speed. It's ambiguous. It could be anything. The light could travel slower there, a little bit slower on the one way, and then, twice as fast on the, all that kind of stuff. Right. But it's literally, if you're into Lorentz symmetry, right. If you're into adhering to Lorentz symmetry, right, you can't deviate from it being equal in the, on the one-way trip. Equal to C on the one-way trip. And then he goes on to show here that if you introduce motion to a frame, you would have to use absolute space to explain it, because they would, two clocks would not be in sync, right? So he's defining here, they didn't have atomic clocks back then, but he's defining like, a little ping pong ball going back and forth at the speed of light. And that's what he's talking about here, and keeping that in sync with another, ping pong ball, doing that at the same rate, but then this one's in motion now. Right, so he shows here that they will not be in sync. And how do we rectify this, my dudes? Because my dude said earlier, he don't need no absolute space. Well, this was how he derives This is how he derives the introduction to Lorentz symmetry, right? So we hit him with a little Lorentz transform. This is the gamma factor. This is length contraction, time dilation we've all heard of. This, under the transformations with the velocity component put in there, will give you how much length contraction and time dilation you're experiencing in your frame, so that you're going to always measure C at the same speed, but somebody, relative to you, would see the velocity difference. So the physical meaning of the equations obtained with respect to the rigid bodies and moving clocks. So this is really important here, because earlier he said, any frame where Newton's equations hold valid, right? And sometimes Newton's equations hold valid in rectilinear uniform motion frames, right? So if that's, so what he's defining here is he's saying, he gives the example, he says, and if a clock A is moved with a velocity nu along A to B, or AB to B, then its arrival at B with the clocks would be no longer synchronous. But if a clock moved from A to B lags behind, in which the order remained at by 1/2 times t nu squared over c, t being the time for the journey from A to B. So he's saying that, they'll be out of sync, and his equations will hold true for a clock moving around the equator, right? Relative to one stationary at the equator. So this is the example he gives. And then he says, it is at once apparent the results hold good if a clock moves from A to B in any polygonal line and when the points A to B coincide. And if we assume the results proved for a polygon line is valid, it is also good for any continuously curved line. What shape does a pop quiz, everyone? What does a continuously curved line shape make? Anyone? So, how dare you? All right. So, and the logic here, of course, is pretty sound, actually. If you extend any curved or polygonal line to infinity, it's not going to deviate from linear. So, logic's pretty sound there. Shout out to your boy Ein. And he goes on to say, to differentiate, that he's not talking about a balance clock, which would be like a pendulum. He's talking about a light clock. So that was the light clock at the equator. All right. So they said relativity was hard, but everyone seemed to get the circle. So like that, that's, I don't know. That's pretty impressive. Everyone seemed to pick that up right away. All right, let's see here. So we got the composition of velocities. So what happens if something exceeds the speed of light? Well, we got a little velocity correction that we can introduce here that will make sure that that never happens. So that's cool. So those are the rules for relativity theory. If anything is going to exceed c, you can make it not do that. And this is where all the equations apply. Uniform transitory motion in any closed polygonal circuit, and especially a continuously curved line, otherwise known as a circle. Very cool. All right, so the introduction to Einstein's theory, right, and the equation he used, and adherence to Lorentz symmetry from it, right, and it being identical to Lorentz's theory, where there's a stationary ether that rigid bodies move through, and, you know, I guess they're not so rigid because they'll contract proportional to their velocity in the direction of motion against that stationary ether. Now, the cool thing about the Lorentz's ether theory is that it incorporates absolute space in it by summation of the transformations. So if you're in uniform transitory motion and you need to get back to the lab frame and find out who's who, dude, you just do a summation of the transformation, and that will tell you the order of events for simultaneity, and that will give you a reference point of absolute space. So the idea that you can Lorentz transform out of a preferred frame is actually incorrect. The complete symmetry of Lorentz is a triangle. Who knew? Who knew? Who knew? So they've only been showing us the linear portion of the equation and just showing the symmetry as like the middle point here in this line. I don't know if you guys can see my mouse. Hopefully you can. But in the middle at the baseline of the triangle, right? So they're just showing us that, but it's actually not. You can do a summation of these and you can find the lab frame. GG. So every Lorentz transformation that's ever been done in spite of an ether theory to show that there's no ether, boys, welcome to the lab frame. All right, so here we have Michelson-Morley, where all of physics was redefined over 6 days of data, right? So hang on 1 second. So it's hard to get a good analysis of the accuracy on the device. It's hard to find some good figures on it, or people putting numbers on it. You know, there's usually like rough estimates we've heard from. There's that one picture. I forget the gentleman's name, but he says that the device was sensitive enough to detect 2 kilometers a second, et cetera, but we don't have anything like, you know, anything really to back that up with or whatever, right? But anyway, what we're going to look at here is a gentleman who does a, what's it called? Fourier transform analysis on it, right? So he's doing a harmonic analysis on it, on the data. And from that, he's able to extrapolate, you know, a confidence level in whether or not the measurements that were taken were actually, you know, null results, or if they were significant, right? If they were that delicious significant figure. So here's the data set that we're going to be looking at the graphs here in a second. And this is in accordance with approximately 8.5 kilometers a second, right? Now we have the Michelson-Morley fringe. So we'll read a little bit here from, I think, yeah, this is from Bourne. So we have a quote here for the accuracy. The precision of the Michelson-Morley apparatus was extraordinary, about plus or minus 0.004 of a fringe. For all details, we address the reader to the book, which sadly the book is $60 for the PDF and $100 for the paperback. Here we're limited to just the quote from Bourne. So I guess he goes into a more extensive detail on it there. But when we were discussing the classically expected fringe, when shift fringe you have to put on the rotated apparatus at 90 degrees, namely the 2A class, approximately 0.4, he says explicitly, Michelson was certain that 100th part of the fringe of this displacement would be observable. So there he's giving the confidence level of the accuracy of the device, right? So their interpretation of it, right? There was two ways that they could look at the data. You could say that the Earth is stationary and they detected a drift, or you could say that the Earth moves really slow, or you could say that there's a null result in relativity theory. So I guess you could say three things technically. Because if you're going to take those on the first order measurement and not transform out of them or do any nonsense, right? You would just have to say the Earth's moving really slow, change all the proportional ratios to the sky, and all that. So anyway, we got some graphs here of his analysis here. Very nice, very clean. We have the data set from Michelson-Morley plotted on a graph here, so you can see the min-max peaks of the amplitudes, what those numbers look like on a graph there. So throughout the day, this is what fluctuations in the speed of light looks like. So when it's going, slightly faster and then it's going slightly slower, and the explanation for that, right, would be what they were hoping for is that it would be going slower by a proportional velocity to 30 kilometers a second. But what we saw they measured was around 8.5 kilometers a second through your boy's harmonic analysis, right? Most people say that it's 6.5. Actually, I've seen 6.5 to 7.5 cited a couple of times and stuff, but like it's generally within this range that it's talked about. And obviously that's outside of the confines of heliocentrism if you were to take that as a first order measurement. And it's too big of a measurement to be link contraction and time dilation. That's why they have to round it to 0, right? So, and just say that you actually can't measure it because you're already contracted. So you're actually just measuring C as C is what they're, what they put forward, right? So we look at the data here, and there are 2 days that are super significant, right? 9 and the 8th, but the whole data set looking pretty good for the significance of the measurements being non-zero, right? There's I don't have the notes up, but there was my dude went as far as to say is he had sigma 5 confidence in what was it, number 9, I think it was. So here we have the same guy who did a simulation of the Michelson-Gale data, 10,000 simulations over the first day of measurements to kind of just plot the amplitudes to see if they would wash out as noise or if they were actual measurements, because some people contend or say that Michelson-Gale-Pearson didn't measure sidereal rotation, but even though there's more accurate devices now. But anyway, just going through this dude's analysis and like looking at what he does, it's like, he's clearly looking at it through a decent lens, because it's matching up with current experimental data when they acknowledge the measurements as Earth rotation instead of ether drift. Like then they're totally good, with the amplitudes that they get, but not with the same ones with an interferometer that's configured differently, right? So what they try to differentiate here is that if the light is at right angles to itself, it's supposed to be only capable of measuring linear motion, and it can't do that. But if you have it complete a closed polygonal loop, then it can measure angular rotation. And when they look at the amplitudes, so like if they plot the min-maxes against sidereal time, right? Instead of looking at a velocity component and just looking at the amplitudes plotted against sidereal time to make a sine wave, they're like, oh, okay, look, this would only happen if we were like, because, you know, their interpretation of sidereal time is how we're rotating into and away from the sun, would be like, okay, you're experiencing velocity addition, right? So to create those fluctuations, essentially, is what they would be saying, right? So anyway, it's just to kind of show that your boy's analysis is on point. And to go back to the Lorentz transformation equation real quick, this was really cool. So the equation actually predates Lorentz as well. A guy named Woldemar Voigt derived this as well for relative Doppler shift. And in his equation, the way that he has the Q there, if you divide by it, it'll give you the longitudinal Doppler shift. And if you multiply by it, it'll give you the transverse. So yeah, it's literally, you know, it's literally a repurposed equation presented as like, you know, a different framework where reality is contracted. You know, it's a mathematical story, essentially. It's been repurposed to, you know, tell everyone that time and space are contracted due to relative motion, even though it explains frequency shift for relative motion with respect to, yeah, boy, the triangle. I'm not going to go back to that slide. It's too far back, but you guys get it. All right. So after 1887, Michelson-Morley, they were like, okay, I guess right angle interferometers are a no-go. Let's hit up closed polygonal circuits or loops. So we got your boy starting with Oliver Lodge around 1910. This is the apparatus he built. Here's some shots of it. So this is an axis and a rotor to spin this up top here. And we'll see the configuration. This is the viewing piece, so he can take a look at those optics, measure those fringes. And this is your boy under the apparatus, you know, adjusting the old speed, working hard. And then he's gonna put his head under there or up there, look at those fringes, and see if he can measure the fringe displacement in accordance with the mass of this rotating steel plate here. The way he was trying to derive it was to see if light would be changed by the mass of a rotating object. So quick history recap. What was it? Fizzy, my boy, did an experiment where he was testing Fresnel drag, where he was a light beam was split in a closed loop, and it would go with and against translatory moving water. And what he found was that there was a proportional ratio measured in the fringes to the velocity of the moving water at 44% going with and against. So he measured 88% of the velocity of the water, you know, irrespective of the refractive index, right? So that was pretty astonishing for them. And the hypothesis at the time was that the ether was a material media, and that when it interacted with another material media, it would experience velocity addition. It would get dragged along with it, right? And that was, you know, substantiated in 1870 something. And from that, this guy was like, okay, cool. Can we do it? Is it affected by mass? Does that work? This guy's measurements were inconsistent. There were, but he basically, you know, got nulls on that. And there was a modern one that was done that was more accurate, you know, better. He got better results than this guy, but still not conclusive. So on testing it on mass. And then oh man, I need the years for these. Oh, cool. The notes are right here. It's low key went with me. Okay. So 1920, a guy named Harris came along. Actually, first there was Sagnac in 1913 after Lodge. Wait a minute. No, sorry. Harris was in 1911. Apologies. This analysis was after. Anyway, Harris was in 1911, and he, following the Fresnel drag experiment, and then, you know, he followed Oliver's experiment, and where it wasn't working with no other refractive media or anything like that to drag. So he tried it with glass. So he came up with his interferometer configuration here, where he has these crystals configured so that the light would go through the crystals, and then it would produce a fringe, right? and he measured according to the refractive index of what he used, and he measured that same 44% ratio, or 88%. And let's see, and then he ended up peacing out in World War I, so peace be upon him. And then we go to Sagnac in 1913. So what we have here is a history of a hypothesis of the ether being a material media, being able to be dragged by another material media. And this was going to be the first time that it was done in open air. So with the Oliver, with what the Oliver guy was doing, his was in air, and he as well, but his was, I don't know, I think it's because apparatus wasn't sensitive enough or whatever, because it just didn't produce anything. But your boy Sagnac comes out here and he measures the fringe proportional to the rotation of the table without the refractive index. So this is the first time that the proportional velocity was measured without where the fringe exceeds the refractive index. So in other words, the air isn't dragging this and then it's measuring the velocity 44% ratio of the air. It's measuring it 1-to-1 against the ether, right? That background medium that they thought was stationary. And would only be moved if it was, being dragged or whatever with another material media. Well, and that's why Sagnac described this as an optical vortex. So he says, it's like, why would you call it that? That's crazy. Well, he goes on to explain, from his rationale, right? Thinking he lives on a rotating globe. He's like, well, the atmosphere on a globe is rotates with the globe, but within that, there's winds that go different directions. So that was his interpretation was that there's an all-encompassing ether that must rotate with the Earth that prevents us from measuring motion like through Michelson-Morley, but you can create an optical vortex through motion, in particular rotational motion. And this will be really significant here in a second, because the configuration I'm showing you here is nice, but Sagnac did a very specific configuration to be explicitly adherent to what Einstein described, and so that he could falsify his theory that there was no need for an ether and you could explain things without absolute space. And it should be noted here that the equation, which I don't have, oh wait, yeah, I do. So we'll go over the equation here. So the equation that explains this and makes the prediction is it doesn't require any transformations. It doesn't require second order effects or any assumptions or anything like that. You can just derive it based off of the length that the light has to travel, the velocity of the rotation over the speed of light times the wavelength, right? So if you know the wavelength and the other factors, you can predict how much the fringe shift pattern displacement will be, and you can correspond that to the velocities, and you could start to, show that you can measure velocities with the, against the speed of light with an interferometer. So that was super significant here. So remember, the uniform translatory motion, any closed polygonal circuit, if the Earth is going around the sun, that's a closed polygonal circuit. So you should be able to measure that. Now, this is the reason that orbits had to change from being, we started with circles, right? And then they said, well, they're actually ellipses and we can apply Newtonian dynamics to them. And then they said, okay, well, here's the thing. This circle's so big that if you extend it to infinity, it's just a straight line. So we can't measure that. But then your boy Sagnac here is showing that, oh, wait a minute, you can measure it directly proportional. So Einstein never commented on the Sagnac experiment or tried to explain the effect or anything like that, right? Other people had to do it for him. He remained silent on it, never, ever publicly addressed it, right? My man published a paper like falsifying his theory. The student never commented on it, right? And let's see here before we move on. Oh, yeah. So anyway, this is why general relativity is so important as well, because again, the orbits are going to be changed from, oh, this is just a big, long linear path to, well, it's actually a geodesic, right? You're actually in free fall. So, from a fourth dimensional perspective. So it's not even what you would imagine it is. You really can't, you double extra can't detect it. You, in the first theory, you couldn't detect it. And in the second theory, you double extra especially can't detect it. As long does everyone, pop quiz everyone, does general relativity predict that you can measure the Earth around the sun? No? Okay. All right. All right. All right. So how do these lads describe all these motions anyway? Rectilinear, angular, velocity, linear. What does all this mean anyway? Well, it turns out all the symbols describe the same thing, and it's all extreme describing change over time. Very cool. Very cool. And they're putting forward that the universe, right, that the laws of physics are differentiating between rectilinear and circular motion. If you're moving in a straight line, the universe, I can't see you. Where are you? Right. But if you start deviating into a circle where there could be a fixed point of oh, dude, the universe can see you again. Okay. And again, here's the kinematics, right? Here's the dynamics. Oops. Here's the dynamics. Here's the kinematics. Right? Acceleration, velocity, position. Anyway. Identical or whatever. All right. So this went on, the Sagnac experiment went unanswered for special relativity. They end up saying that, well, because it's a uniform translatory motion, even though it's explicitly defined by Einstein that it would apply, we're going to ignore that, never acknowledge that point, and just go ahead and say that we know that uniform transitory motion in a circle is an acceleration, so it has to be governed by general relativity, and everything is okay now. And don't worry, boys, we're going to get super deep into that. But before we do that, we're going to look at Ruyang Wang's experiment, where he's explicitly using an interferometer configuration to show that it doesn't matter if an interferometer is at a right angle to itself, if it's in a circle, if it's in a polygon, if it's in a dodecahedron, doesn't matter. So what he's showing here is that the delta L, right, the effective length of the fiber here, is what the fringe is going to be relative to. It's not relative to the detector, where if that were true, then the full length of the apparatus would have to be accounted for, or at the very least let's see, not the parts that cancel out, but at least this bottom part, like the whole thing would have to be. If it was relative to that, then it would be you would have to add this length. Right. But the delta L here is literally just this top portion here and this to this top portion here. So this fringe is only proportional to this part of the apparatus. And it can't be relative to itself if relativity theory is true. Relativity theory predicts that this measures no fringe. Yet we're looking at my dude measuring the most linear fringe displacement anyone's ever measured in their life. So, huge contradiction to relativity theory, and just in terms of a linear apparatus, right? Let alone a closed polygonal circuit, which we'll come back to in a minute here. So just to show here, MMX, light going at a right angle to itself, definitely still viable to measure things, although it will not be as accurate. And the reason for that is the closed polygonal circuit has infinitesimal points upon which it can make the measurement with, and it has to be in a specific alignment with it, and it only has on the rebound points of that to get it, so it's going to get less or whatever, right? My man of stone. Thank you, sir. Okay. So this is the the configuration of the Sagnac apparatus from 1913. If you'll notice this S here, we have the polygon that the area of light makes as it traverses this closed polygonal loop, right? And then it's in uniform motion as described by the holy scriptures on the electrodynamics of moving bodies by Albert Einstein. So this is specifically why he did it like this, because he could have did it in the how I made it in the diagram where it's nice and symmetrical, right? But he's showing here that you don't need the symmetry to do it. All right. So we have, let's see, what year was Nicklaus? 1 second. Got to scroll through the notes. 1990 thrice. What a good year for interferometry. So these gentlemen were doing an experiment with a neutron, I think, or yeah, whatever, you know, we'll come back to that later. But what they note here in their experiment is that it's a big list of people who try to derive an explanation for the Sagnac effect as a consequence of relativity theory, right? Because relativity theory predicting that the speed of light is constant in inertial reference frames, in frames that are in uniform transitory motion, that you will, and that because of the constancy of the speed of light, there's link contraction, time dilation, and of course the principle of relativity of simultaneity, where there's no cohesive timeline of events. If you were in relative motion, you won't, two events that occur simultaneously will not occur simultaneous for you, but they will for, you know, someone who's stationary, right? So the idea put forward is that in physical reality, right? Like, I think we all understand that concept, but like they're saying that in physical reality, it's different. So in other words, my boy Xavier likes to give an example of, suppose you have a bomb that will go off when it receives a signal at the same time of its, it's like, it has two receivers on it, and when it receives a signal at the same time, it'll detonate, right? So the signal is sent, there's a stationary observer, and there's a moving observer. Do you think that the bomb won't go off when the wave hits the receivers at the same time because the moving observer in his reference frame would see one of the waves hit first relative to the other one? Does anyone here think that the bomb wouldn't go off? Because relativity theory, like that's literally the backbone of it. No, you'd be super dead. Yeah. Yeah. So anyway, yeah. No. Yep. Yeah. Because in lab frame, you'd be dead, straight iced. Right. We'd have to introduce a fictitious Shane. Yep. Yeah. No worries. No worries. No worries. All right. So let's see here. So anyway, of note though, he cites Paul Lefebvre, right, as the Frenchman who derived the explanation under general relativity, right? Because we're sometimes told that because it's an acceleration, you got to get my boy general relativity in there. So he puts forward the idea that using tensor calculus, that you can the print and what general relativity is based off of, you can conserve the energy of the rotating device fully as a gravitational field, and that would contract proportional to the velocity, giving a physical explanation to why there's a fringe displacement. We can't hear. Oh no, they can't hear the boys. 1 second, let me fix the audio. No. Yeah, nobody said too much so far, I don't think, but 1 second.
Just for the crowd, Paul Lefebvre was actually Paul Langevin. He's on the left there.
Paul Langevin. Thank you. I'll be right back. I'm going to close Discord and reopen it. It's doing the choppy audio thing. I got to...
I hate when that happens.
Yeah.
Can you pronounce it one more time in case I wanted to like actually try?
Yeah, Paul Longvong.
Damn it.
Well, I kind of like blah, 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 blah. It's got some swing to it.
The bad thing is it's in my head now is blah, 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 and I can't like commit
You can't
a real
undo
word
it.
to it. So yeah, it sucks.
You've been infected. So
That's
is
why
it
I'm trying to
Paul-
get it right. Okay.
Paul
Dude,
Longval, right?
I thought Lavu and Lavon were like two different people for a while. I'd be like reading and I would read Lavon and I'd be like, well, it's not Lavu, so this must be someone different.
Yeah.
And it's not Fizao.
Yes. Physio.
Physio.
Physio. That's right.
It's
Physio.
definitely not Physio.
Physio. Young Physio. All right. So anyway, that's the story of him deriving that. And they went along with that explanation for a while, but we're going to see a huge refutation to that later, which they promptly walk back. And then we're going to look at some analysis of its subsequent. All right. So
we lost a little bit of your audio gain there, Alan. You're down a bit now.
Oh no. 1 second. Oh, how is it now? Maybe it was because I was facing away from the mic.
Halfway in between there. A little better.
Son of a gun.
I turned you up a little bit on my end,
Oh shit. All right, give me 1 second.
which it's not a problem for me, but
I'm good.
No, I would just keep going, man. That's good.
Nah. Gotta at least check. Make sure it's on the right mic.
sounds
you're
pretty
good.
good.
All right. Okay, so here we have, let's see. Nice. Okay, so in the battle of who can explain this the most bestesses, we have Post here in 1967, who is trying to use special relativity to explain it. And he says here that if you separate the electromagnetic processes into their respective fields, so the electric, magnetic, etc., right? And you bind those to what he calls free space, and you have free space do the old rotating, that will drag the corresponding fields such that it will produce the fringe for the relativist, like magic, right? Now, there's also let's see here. So that was his explanation for it, giving the mechanism. Okay, yeah. So what he's saying here is essentially like instead of using special relativity for acceleration, he's using a centrifugal potential as the mechanism to spin free space around and all that, akin to how general relativity uses gravitational potential, right? So it's not the same mechanism consistent with relativity or with special relativity. And this is going to be a conflict because there's something called Thomas precession, which we're going to get into here in a second, which this would conflict with. Let's see, because this guy goes on to say that he can actually derive Thomas precession from his derivation there. And this was checked by Ron Hatch. Now, I'm not going to, I don't know the math good enough to do that or whatever, right? But, Ron made a note to say that was not true, that he could derive Thomas precession from his rotating free space conception. So shout out to you, boy, Ron Hatch. Let's see here. We'll come back to Post here in a minute because he's going to with the Thomas precession stuff. So we're going to move on to another explanation that was given for general relativity, but this one was like all these explanations that these people try to give are inconsistent with Michelson-Morley and Michelson-Gale-Pearson, right? They can't explain why this is giving a measuring motion and the other one isn't. They can't quite seem to agree upon anything. And then we have Ali and others, and shout out to Ali, who's been trying to get relativity into meaningful technology since the 70s. He's been trying to get it into GPS for a hot minute. So let's see here. What does he say? So check this out. He gives a derivation for it, and then the way that it works, though, it's with respect to the central axis of the Earth. So they're not even sure if an observer on the Earth would actually measure that, because you would be in the proper time frame, because you're rotating, you're in the acceleration frame. So you wouldn't measure it because you're link contracted time dilated. You would have to see it from the center of the Earth. So they're literally not even sure what they should measure, boys. All right, and this is a configuration that was done in 1927. Sorry, these are out of time order, but it's just the measurements are really what's important. It's just consistent repetition of different interferometer configurations that explicitly falsify relativity theory. So, this configuration, the symmetrical version here, and then he's got optical media here as well that he would do the experiment with, all showing the proportional ratios corresponding to everything. Like, they've always been trying to figure, this is why they've been trying to figure in the Sagnac effect into relativity theory, because relativity theory is a theory of second order effects, right? Time dilation and link contraction are really, really, really tiny effects. What's being measured here are first order effects, right? Directly proportional to the velocity. Oops. Go back. There we go. All right. And then just to make sure everyone's on the same page, right? Why this is significant. Post in 1967. To be consistent with the principle of relativity, one has to demand that the Sagnac interferometer and the ring laser cannot lead to a fringe shift or a beat frequency if the equipment is in uniform translational motion, right? So all the arguments that we've made over the years, like we've been at war or something, we've been arguing this for a while now, and just like, here's like the substantial, like within their paradigm, like this is, they can't explain it, it's never been meaningfully explained. And if I remember, somebody remind me, we will look at the two most recent, quote unquote, refutations / absorbing the Sagnac effect into relativity theory. And we'll see where they go wrong too, because it can't be done, guys, no matter how hard they want it. Let's see here. See that there was a message.
It strikes me that the reason that they're measuring very, very, very tiny shifts has to do with the proportionality of those velocities to the speed of light itself. That where everything here is happening so much slower than the actual speed of light, that your interference fringes are very hard to detect because they are a small fraction thereof of that velocity up top. Do I have that correct?
What's that? Yes. I think you said that the fringes are small because the velocity they're being measured against the speed of light is small comparatively. Is that what you said?
Yeah, that they're a very small fraction of the speed of light that the realm we're measuring here.
Dude.
Magnitude reflects
Dude, the smallest, bro. And then it gets even smaller than this because they found out a way to do it with what was it? Some sort of X-ray emission that's basically 10. Well, yeah, we read about it. It was 10 times 10 to the minus 10, I think it was. It was like, that's crazy.
Getting out the decimal points.
Yeah, they get their decis out, but at least these are physical measurements that can be substantiated. Like that's what I like about it, is you can actually, given the metric or whatever, right? They actually have a counting mechanism for it, so that's nice at least. Even though it is insanely small. So let's see here. Okay, yeah, so specific procedure for dealing with rotation here. So we have Born was clearly wrong. Feynman shows the general theory to incorporate the infinitesimal structure of special relativity, right? So there was some other derivations were trying to explain the Sagnac effect, have to use in general relativity, you can set the input and boundary conditions. So what they will do is they have a flat space-time metric and a curved space-time metric. And the flat space-time metric, which is more associated with special relativity, where you're not accounting for gravitational effects, where it's just flatness, it's not something you're factoring in. They'll take it to an infinitesimal like same exact situation with curved metric, but then it's just like, but you're making it flat and just pretending like what, like just, you know, let's not beat around the bush, boys. So this guy tries to, let's see, we'll just read off the quote here. So the Lorentz transformation by Goldstein clearly spells out the method for handling acceleration. So this is going to be the introduction to the Lorentz boost for Thomas precession. So we imagine an infinity of inertial systems moving uniformly relative to the laboratory system, and one of which instantaneously matches the velocity of the particle. The particle thus is instantaneously at rest in an inertial system that can be connected to the laboratory by Lorentz transformation. It is assumed that this Lorentz transformation will also describe the properties of the particle and its true rest system as seen from the laboratory. So what this means here is... cool graphic, right? So this is the introduction to Thomas precession. They say that an electron orbiting a nucleus, you know, has a little magnetic field, and that magnetic field is catching a little drag or something, and it's precessing, right? And to explain this, due to its acceleration, they bring in the Lorentz rotation, and we'll get into what that looks like on a coordinate system to explain what exactly they're rotating to conceptualize this. But let's see. But will this be able to explain a fringe shift pattern? We shall see. So anyway, here's what Thomas precession looks like, right? You're just inverting the world line axis with the direction of motion at any infinitesimal points that you decide, so that you and in doing that, you create the equivalence of a linear transformation. So doing 2 Lorentz boosts is equivalent to a linear transformation. So they're saying that they can fully handle a uniformly rotating so we can do it, but we definitely can do it, but only if it's a really tiny electron and not like an interferometer or anything, right? Because the issue here again is that this doesn't produce link contraction and time dilation for an interferometer rotating at 13 meters a second on a turntable, right? So here is the classic derivation for it, right? Your delta t, right? The change in time, it's going to be 4 times the area times the angular velocity times, or over the speed of light, and then times lambda, which would be your wavelength, but I didn't include that in there. But that would just be relative to whatever you're using to make the measurement with. All right. And it explains it fine. Proportional ratio, first order effect, V over C, essentially, right? Let's see. Surely a hero will emerge to explain the Sagnac effect as a consequence of relativity theory, special or general. Turns out that will not be the case. It was shown by Kelly in 1995 that the special theory has no relevance trying to explain the Sagnac effect as seen with the earlier speeds as shown. What you can do is you could take a disk, extend it to 1 kilometer, rotate it as fast as you want, and it'll never produce a fringe shift proportional to what is measured on the first order with the second order effects. It'll never link contract and time dilate enough to actually physically explain the fringe display, why that light is out of phase. It cannot be done, no matter how big or small you make it. All right. And then this is just so we talked earlier about the orbital mechanics changing, right? From circles to ellipses to, oh, well, it's a really big ellipse, so it's pretty much a straight line, to, well, here's the thing. Reality is actually bending around your free fall. So this is where all this comes from. Like, this is the introduction into this, where he talks about a path, a linear path being curved linear, right? So this is just word magic, relativity of simultaneity. Something can't be simultaneous and relative at the same time. It's either simultaneous or it's not. You can only be linear. You can't be curvy linear, right? That's insane. But this is what has to be introduced to maintain the idea that the Earth is moving around the sun, and that and more importantly, that there's no ether. So let's see here. So just to give a little conceptualization visual for the boys of what a geodesic looks like, this is what it looks like. Traveling on the old, we've all seen the old gravity well thing, right? This is This is what they tell us, right? But you would never be able to tell from you can only see this from like a fourth dimensional outside God view, right? From your path, you would literally just be free falling in a straight line and basically not moving. All right. So remember when general relativity was thought to be the cause of the Sagnac effect? Well, insert 1942 with Dufour and Prunet. They did a configuration of a Sagnac apparatus where they, using 45-degree angled mirrors, they could have a stationary disc and a uniformly rotating disc, and they had it such that they could have an observer on the rim of the disc, and they could also have an observer fixed to the lab wall. Now, let's see here, when they do the math and relativity, right, they assume this symmetrical position because let's see, to make the path length or whatever is irrelevant. They just need to make it whatever the area is so that it'll fit symmetrically. It's like they don't care that, like, you know how Sagnac did that configuration where it was in different lengths and stuff. The way that they need to the way that they solve it demands that they take this position at the center so that they can put the path length, in a circle around it relative to that center point. And that's important because relativity theory is a theory that says that the general theory in particular with general covariance says that any old frame will do. Any old frame will do her, right? So you should be able to derive it from the observer on the wall. You should be able to derive it just as good as you can derive it from an observer on the rim, right? And so we'll get into that here in a minute. So anyway, this is the configuration they used, and we'll look at some pictures of the setup here. This is what it looks like, or this is what the path of the light would take. You can see it would go here, recombine for your boy at the wall, or you would have your guy on the side there. This is the lowest quality picture I could find, and hope everyone enjoys. But this is what we're looking at here. So this is the top disc that's stationary, bottom disc that rotates uniformly, and there's a lab wall presumably right here. So what the lads found was that the classical theory was fully able to predict the fringes, has no problem. And the classical theory, measured the 0.053 of a fringe. And then the general theory using the lab wall shows 0.005 of a fringe, 10 times smaller than what was actually predicted and measured by the classic theory. Thus showing that you have to use a preferred frame, right? And Paul Leveux makes the argument that, well, because it's in a rotating device, gravitation is involved because you're getting pulled to the center due to this other fictitious force that we invented to counterbalance the outward motion of centrifugal force. So let's see here. After that, So anyway, he says that because of that relationship, you have to invoke the center position and not use the lab wall. And that's just a way of saying, well, general covariance is not true, but it's also true at the same time. So anyway, he got slayed here. There's no answer for this. General relativity is unable to, like the substantiation of general covariance, any frame is as good as any, because you can treat acceleration as gravitation through tensor calculus. When you invoke geometrically convenient positions, that you say are geometrically convenient, but what you really mean is if you don't do it in that specific way, your theory completely fails. All right, so there was supposed to be an image here, perhaps. Nope, this is just a quick recap. So Sagnac and the boys conclusively just body bagging general and special relativity, forever. There's never been a cohesive explanation for the Sagnac effect put forward that can physically explain the fringes. Just to recap here. All right, so now we're going to get into a little bit of GPS. Okay, yeah, so 1 second. Before we move on, let's talk about the Thomas precession and let's see. Okay, yeah, so if they're going to use Thomas precession, right, then they can't explain Michelson-Morley as a null because there would be a measured amount. And they, like, none of these things are ever consistent with anything, but because of the way they've just, the Earth's motion is just taken for granted so much that they just have these glaring contradictions out there that can't be rectified. And then they'll have like an isolated mathematical solution for something, but it contradicts something else. But they're like, but they forgot about that, because it's just assumed that the Earth's in motion and that it doesn't matter, blah, blah, blah. Right. All these are givens. So they don't, it's just not really acknowledged, but none of these are able to explain any of that. And it's only through kinematic analysis that it's able to make predictions that align with anything. Right. But when you actually go to measure it, it doesn't always work out for them. So here we have GPS now. Because we're told that special and general relativity are, explicitly work because of these theories, right? If those theories were not true, then GPS wouldn't work. So we'll read a little bit here. The GPS tracking station clocks verify the direct effect of the gravitational potential upon the clock rate. The tracking station requires the clocks to adjust their time at a height above sea level. Interestingly, they do not require an adjustment for their latitude. The oblateness of the Earth due to its spin rate is such that the effects of the extra gravitational potential, the greater equatorial radius, upon which the clocks at the equator are precisely canceled by that greater equatorial spin velocity, right? So
What a handy proportionality.
dude, so my man just swooped up all the deflections of the verticals. We'll come back to it here in a minute, but we're just establishing corrections that are in the clocks right now for GPS. But so let's continue on here. So this is from A.G. Kelly, who wrote to the International Telecommunication Union. The CCDS wasn't able to figure out what that acronym comes out to, but it's some international clock synchronization standard agency. So anyway, he writes to them about the corrections that they make. So he says both bodies in the three collection or name three corrections as relativistic. These are the velocity correction calculated under special relativity for use when transporting the clock, right? So the old relative motion. And then we have the correction for the difference in the gravitational potential under the general theory, right? Now this correction here, before we move on real quick, I kind of glazed over that. So this is a Sagnac correction that keeps the clock in sync proportional to its own velocity. And they actually have to apply this not just when transporting them terrestrially, like on the ground in trucks or in planes, but when they're quote unquote free falling in orbit around us, in their local inertial frame, where the speed of light, where c is supposed to equal c always and forever z's. But yet there's a correction here. What they're calling this a relativistic correction. It is not, right? This is the first order Sagnac correction. We've established that a velocity correction of that magnitude is not in the dominion of special relativity. The correction of the difference of the gravitational potential under general relativity is outside of the scope of this paper, but he's just noting that the correction is in there where they say that the clock rate also oscillates a little slower due to the equigravitational potential at its orbiting altitude. And it seems to be a uniform correction, no deviation for the latitude dependence like there is on the ground with the equigravitational potential difference with theodolites, which we're definitely going to come back to. So this latter correction is the Sagnac correction and has nothing to do whatsoever. Oh yeah, then they have another correction here, right? So then they have a third correction that is for the Earth rotation. So this is where they say that they have a correction from satellite, space vehicle to ground receiver, right? They're saying that this is a Sagnac correction. And again, we've established that the magnitude is outside the confines of special relativity. But this is how they look at it, or this is how they've had to dress it up. So the latter correction is the Sagnac correction. It has nothing to do whatsoever with relativity. It is a correction necessary because light does not travel around the globe east and west at equal times, right? So there's a preferred direction that they've been measuring, right? All these interferometer measurements that claim to be measuring sidereal time show a bias in the direction that produces the measurement. And that is what that's what they're correcting for with GPS, or that's what they're saying, right? So they're calling it Earth rotation. We would call it ether drift or ether wind. So invoking special in the general theory to explain the Sagnac effect is like claiming bouncing a child's ball requires the special theory to explain it. So a simple first order effect. It's a simple first order effect. You don't say. Indeed, the president of the CCD wrote to this author agreeing that the Sagnac effect is not relative. The Sagnac effect correction is not relativistic. So shout out to that guy. So anyway, real quick. So how are they Sagnac correcting all of a sudden? What are they doing, boys? Well, remember the coordinate system inversion that we talked about earlier, inverting the time axis, which is perpendicular to the direction of motion, right? They just swap those out. And if they don't do that, they say that they'll be off by 30 meters to the east. So in that correction, right, that's not a Sagnac correction. That doesn't explain why there would be a variance in C, right? Not to the first order. So that's not what they're accounting for. Okay, so let's see here. The old Lorentz boost. Sagnac, okay, the measurement taken with the range measurement equation. Yeah, so check this out too. So the ground receivers, the measurements are taken with the range measurement equation, right? So it's deriving the time from when the signal was sent and the position of the location of the satellite. Let's see, with respect to how long it took to get to the ground receiver. And there's a variance proportional to the velocity of the ground receiver, regardless of his motion. If he's traveling in a circle, or if he's traveling in a straight line, it all works out proportional every time. It turns out the universe doesn't differentiate between the two. So these are trilateration measurements too, right? So these are one-way measurements, right? Space vehicle to ground receiver, and the calculations are based off of everything that's encoded with the signal that was sent. So these are literally one-way timing signals for the speed of light that show a variance to the velocity of the receiver, or they would not be able to accurately derive a distance, right? So these are not Sagnac corrections in the sense that they're relativistic corrections, right? These are first order classical mechanics, ether wind, velocity, ether mechanics, right? All motion being relative to a fluid background medium, right? This is what would facilitate that mechanism for the measurements to be made, right? That's why this is important that Einstein said, oh, we don't need a luminiferous ether, right? And those words specifically were associated with the physical media aspect of it being the necessary part for the thing for electromagnetic propagation to occur in, right? So that equation earlier we looked at with Maxwell with that oscillation rate, that's an oscillation rate in a medium, right? And that medium in the equation that he was using for epsilon and mu was electric permittivity and magnetic permeability. So, it's like, what's it waving or whatever. So this is why he had to remove that, because all motion would be relative to that. And you could make measurements against that. You could definitively know if the Earth is moving or not. And that's why after 6 days of data, they redefined all of physics, because they knew what they measured, because they knew that they could measure uniform transitory motion, right? They've known the whole time, boys. All right. So we're going to do a quick recap on the ECI and ECEF frame. The ECI frame is the old fictitious frame. I call it the ether-centered inertial frame. The reason being is they use this frame as an absolute point of reference to make their measurements, right? Because as we went over earlier, GPS is a timing measurement system. So they're making one-way trilateration measurements off of the speed of light, and without raising any alarms, right? They need a way to derive the measurements and then add in a little Earth rotation correction after the fact. So they have this fictitious frame that they invent here. That's stationary, doesn't move. So in their model of moving through the cosmos, this frame would experience 6 months of day and night. So it's not, it's just, it's literally, it's literally just an ether frame. It's just used for
the frame of mathematicians pretending to be physicists, or did I get it backwards? I always fuck it up.
Essentially, yeah, it's just used for calculating the distances to make everything proportional to, right? That's where it starts off the coordinate system with. And then we have the ECEF frame, right? So that's where they say this is the ball frame that they live on, where they rotate. And they instead of taking the measurement from with respect to an absolute frame here, they put it on the ground receiver and act like it came from here to here, and like this is like the final product of it. Like they're like, this is where it works, even though it was taken here the whole time, right? They introduced a different way to look at it real quick, and then brought it back to where they were at, and then they're like good to go. Now, Alan, aren't these coordinate systems globes? Well, as my boy Shane pointed out, we live in coordinate system simultaneity. where all these coordinate systems are relative and valid at the same time. So we have Cartesian, rectangular, cylindrical, spherical. So if we lived on a plane, you could project all of this above us as it was happening as it's happening on a ball and going around a ball, or you could have ellipses going over rectangles. It doesn't matter, boys. It's all the same. To act like you couldn't math this out on a plane is insane. And we're going to get into the equigravitational potential corrections here in a second, which I think are super significant in establishing the planar nature here. So here's some more examples of coordinate systems that are all equally valid and equal. All right. And then again, real quick, because GPS is a time interval system based in deriving distances as a ratio of the speed of light and that time difference of when signals it was sent and received, you can if it wouldn't matter what shape of anything we lived on, the distance it derived would be accurate either way. Doesn't matter what coordinate system. So, okay. Now, so we're going to get into scale invariance a little bit. That's something we talk about often because that's where when you change a constant in a system, one of the variables, right? It will the rest of the system, if it scales proportional, right? That means that the system scales invariantly, right? So what you would do here is like, since the distances are all based off of angular sizes, right? Of was it 0.53 degrees angular size, you could say that the sun was it 86,000 miles wide, 93 million miles away, or it's was it 486 miles away and 33 miles wide, right? It's all proportional. It would all scale proportional to the distance, and you would never, if you can't verify it, you would never know. So any distance would be just as good as any. But the way that the solar system is scaled out, the way that they've built the model, if they change that number, everything else would have to change. So because it's all based on the periodicity. All they would have to change distance wise is they would just have to say, oh, you know what? Instead of Saturn being 860 million miles away, it's only 400 million miles away. We just didn't know, right? Like whatever distance they would change it to, everything would scale proportional, and you wouldn't know because the reference is so large anyway. Like you wouldn't know the difference between 400 million miles and 800 million miles. So that's how that works. So anyway, to bring that back real quick before we move on, what I think is happening with GPS is like they send out spoof signals for a coordinate system that isn't where where the craft is actually at. They send it from like where it would be if it was actually at an altitude of 20,000 kilometers and all that stuff, right? And then everything is derived proportional off of that because it's just cooked into the way that it's sent. And we'll get into the corrections that they make as well, or like what that Sagnac effect correction lends them the freedom to do. Okay, so for the equigravitational potential, there was an experiment in 1960 called Pound-Rebka, and in 1965 there was Pound-Snyder. Before those two lads came along, there was a large debate about gravitational redshift when it came to astronomical observations. Nobody could really agree on a cohesive way that relativity, that the general theory would predict that how gravity would affect light. And then they had trouble figuring out, a good spectrum to analyze it in. So they went from different spectrums to anyway. There wasn't any, cohesion in it really. So this laboratory experiment is going to be super significant for them. 1 second. Okay. So the experiment was going to be really significant for them because it was going to substantiate the prediction, in the lab where they could measure it from general relativity. So the setup was they were in a tower of 70 feet on the first experiment. The 65 experiment was 75 feet. But anyway, they had a tower 70 feet and they had a detector at the top and they had an emitter at the top and a detector at the bottom. So they were just emitting electromagnetic energy from the top. And then they had a Mossbauer detector at the bottom. And what a Mossbauer detector does is it converts electromagnetic energy into an electric signal based off of its frequency. So a certain frequency will produce a certain electric signal frequency, like a ratioed out. So it'll be proportional to what they're reading, right? So what they predicted was that at 75 feet, the gravitational potential of the emitter would be of the starting wavelength and frequency would be, its original wavelength or whatever. But because of Earth's gravitational field and under general relativistic effects, the conceptualization of the gravitational field in that regard, like essentially making it like a medium that you're traveling through, and it's denser as you get closer to the surface. So they're saying that as you're getting closer to the surface, there's going to be a frequency shift in the light because you're interacting with that gravitational field, like the density of it, the strength of it, and it's going to physically change the frequency of light. And this detector will only accept a certain frequency. So the detector at the bottom isn't set to detect the frequency that the energy is emitted at. It's set to detect the frequency that it would be if the gravitational field shifts it such of the prediction of general relativity, right? So they do their experiment, they send it from the top, and they send one from the bottom going to the top. They do the vice versa, right? And the detector gives the measurement. Now, in their paper, they say that this isn't proof of general relativity because the classic theory predicts the same thing if the energy that they emitted traveled faster as it was falling, as if it fell at 9.8 meters per second squared, right? So as if it accelerated slightly faster, that prediction makes the same frequency shift. And thus, there is no distinction between classical and general and relativistic physics from this experiment, from their own words. And then they did the experiment again in 1965 using a gamma ray instead this time. And the purpose there was because a gamma ray is electrically and magnetically neutral. So it was to eliminate potential interference of like the apparatus, Earth's magnetic field, what have you, anything like that. Ambient background gobbledygook. So they did it with the gamma ray and they got the same measurement, but same conclusion. They didn't alter their stance on it. But they suggested at the end that they should do a detection with atomic clocks at the top and the bottom so that they could time the flight and see if it is the speed of light that's accelerating or if it's remaining constant, but it's frequency shifting due to the gravitational field. So it would arrive at the time expected by C and not C plus V, right? So they've established here that there is a gravitational gradient that needs to be accounted for. Otherwise, it's going to frequency shift light. So now that we've got the history on, and those gentlemen were given the Nobel Prize for proving relativity theory in papers that explicitly say, like, the conclusion is not that it proves that requires more et cetera, et cetera. But needless to say, science needed a hero to, you know, substantiate general relativity as a physical mechanism to explain astronomical observations. And you know, once they got people to, you know, get the agreement on that, they could start applying a uniform way of looking at the astronomical events, right? Or, you know, like basically just splitting starlight in a prism and then looking at the colors and seeing, you know, oh, is it more red or blue? Oh, is relativity more true or less? Is it, you know, or whatever, right? So that's what they're going with. So anyway, we have the satellite here. So this diagram, sadly, I didn't make it, what do you call it, proportional. But let's say that this satellite is at the 50th latitude, and there's an observer here that this blue line is at the zenith, or the satellite is at this man's zenith at the 50th parallel. So this signal is coming straight down to him, and then the signal is also being emitted at the same time to a lad that's at the 40, you know, the 40th parallel, let's say, right? So because of the contour of the old ball, right, and the signal being emitted at the same time, this gentleman here that gets the blue shift, right? Okay, so suppose maybe there is equipotential gradient, right? And this dude's going to get his measurement at that zenith, at that latitude, without requiring a correction. Well, this dude is going to be at a different equigravitational potential relative to that satellite when it sent that signal at the 50th. And he will require a latitude dependent correction. That's what Ron was putting forward earlier about the latitude dependent corrections, right? So what had happened when they made GPS was, if the equigravitational potential geoid model were true, and there was all these discrepancies that they went around measuring and had to deflect the vertical as they pleased to compensate for astronomical phenomenon not aligning with their graticule, then when GPS was established, they would have gone around to every every one of these gravitational points, and made corrections for that potential difference. So to handwave dismiss that, you know, Ron says because of the oblateness matched with the geoid, the gravitational model, right? It's offset through the rotation of that through rotation of a stationary gravitational field. So that's a cool story. Or we live on a plane, and these are on a plane above us, and there's an equipotential gradient between us, and they're sending signals through that. What do you guys think? Pausing for feedback.
Well, I think that the latter is going to get me castigated by society for daring to think outside of the globe. So I'll go with the former.
I see.
But no, it's a pretty good theory. Makes sense to me.
Yeah. So yeah, they go as far as to say is that when they're on the ground, they have a plub bob, and it's actually not going down to the center of the ball like they think, right? They're saying that because of the gravitational potential difference, they have to actually correct for their plug bob being off, right? So to be perpendicular with the geoid, right, the gravitational model, they have to offset. Now, if that's true and it's to the magnitude that it's physically deflecting a plug bob, it absolutely mandatory has to be corrected for in the frequency of light. If they could measure it at 75 feet above the Earth's surface in a tower in a lab in Harvard, right? Like there is a shift, but it's all of a sudden it's equipotential. It's all good. Doesn't matter. What could that mean? Are we looking at two equipotential planes? These are things we all ponder, gentlemen. All right, so we get into the corrections for GPS, right? So we're told that we have to introduce relativity to GPS. That GPS would not function without it. We went over earlier the equigravitational potential correction. We went over the Sagnac correction and the Lorentz boost Sagnac correction variant. But what are they actually correcting for? Because we know that time dilation isn't of the magnitude to correct for the velocity of a moving clock. So what are they really doing? Well, Paul Marmé points out in 2000 that the equations that they're using are just the dressed up Sagnac equation. So we got the old familiar components of length, velocity, and the ratio of the speed of light. What do you know? And let's see here. So earlier we talked about Einstein's one-way speed of light and how people have an interpretation that, oh, well, you know what? Maybe it's possible that the speed of light is different. And because we can only measure it on the two-way, we can never really know, right? Well, okay. Einstein clock synchronization is based off of like the protocol that they came up for it based off of his rules, right? Was that it would be the same going in one direction. So the way they have the timing set for how they calibrate atomic clocks, there's a specific protocol set up, which should be in the, nope, we'll get to that slide here in a minute. But the way that it works essentially is once they have it synchronized, because the clocks are in an inertial frame, they should never require any corrections. They shouldn't be correcting for its velocity proportional to the center of the ECI frame. That's crazy. Why would it do that? Why would it be, oh wait, unless the ECI frame is the Aether centered inertial frame. Those tricky lads. All right. So, we got some experience. So they were testing out, GPS wasn't built overnight, boys. You think the Great Wall of China was built overnight and Rome was built in a day or whatever? No. GPS was built on figuring out how to get these clocks to stay in sync. So obviously there was a protocol established for Einstein synchronization, and they started experimentally testing that based off of the one-way speed. And what they found was that it would work sometimes, but then the clock would fall out of sync, and it turned out to be a velocity issue. And then what they would do is they would sync a clock up and then move it to a location and then find that it was out of sync. So what they would do is send a signal with a Sagnac timing correction on it to offset it, and then it would be in sync again. So like they could never quite seem to figure it out for a while unless it, as a relativistic synchronization. So when Kelly was emailing writing letters to all the boys at their respective clock synchronization organizations, that's what he was ascertaining about the corrections, that they're actually all just Sagnac corrections. And he points out here about the meridians, right? So among the list of corrections, there is a correction involving a parameter taking into account how many meridians the Earth is crossed by light or a moving clock by nu at two locations. And what he's saying here in reference to the ground stations is that Lorentz flip, that, that Sagnac correction is the meridian. He's calling that the meridian correction, essentially. Right. So for a while, I was mistakenly saying that this was like a separate correction, but this is the Sagnac correction. And you can also, Yeah. Anyway. Let's see here. So the correction of the light clock. So we'll get it into what the implication is for making the Sagnac correction here in a second, and what freedom that gives them in terms of distances and whatnot. But we see that the correction of the clock is, just identical, more Sagnacs, right? So we're all Sagnac'd out of our minds. So here we have another excerpt about rotation and GPS and the Sagnac effect. So he says, pretending that special relativity does not apply to rotation, while at the same time applying it to daily experiments like the GPS system, we have a far greater amount of rotation than the Sagnac experiment. It's indefensible, right? So he goes on to show how much the Earth would move. based off of satellite corrections, right? That they're saying they're making, but they can't explain it with a rotating interferometer. So the original Sagnac test on Earth would have turned 2 times 8 to the or times 10 to the minus 13 orbital degrees during the test. During the GPS around the world test at the equator, the Earth would have turned 10 million times that amount turned in the Sagnac effect or Sagnac test. And they're saying like, we have to correct for it for that. It's a relativistic correction, but they can't account for it on a rotating interferometer that's rotating at 13 meters a second. We could be forgiven by saying that this is very biased selection of what is termed an inertial frame. Let's see, the results are the results of the same spinning disk for any radius with a disk approaching infinity. The results approximate a straight line. So again, here we're just kind of reiterating on the on what was already established about extending it to a straight line. It doesn't apply, it has to apply to the Sagnac effect, but it can't explain it. So obviously falsifying special relativity as the causal mechanism. And then he goes on to say that to be consistent with the special, this was the quote from Post that I grabbed earlier, because I went back and had to grab this for the full context of it. But so to be consistent with the principle of relativity, again, one has to demand that the Sagnac interferometer and the ring laser cannot lead to a fringe shift pattern because it is in uniform translational motion. Yet GPS signal receivers, they're saying they have to Sagnac correct for that from when the time the signal was sent to received. When they did the around the world one where they were like relaying a signal, like, dude, come on, boys. So the Einstein clock synchronization protocol is that assuming that the speed of light is the same on both trips on the way there and back, they can set up a situation where when the moving clock alpha intersects with the stationary clock, they can send a signal that encodes that time to the clock beta with the time that was sent from clock alpha, right? And then the moving clock beta receives the signal and then applies a half-time correction to the amount of the travel time from C. So again, right, it's specifically based off of the one-way speed being C as well. So the moving clock B, and then the moving clock B will then, and the stationary clock will then be synchronized with their time, with the stationary clock A, right? Once they get their corrected signals. So that was the protocol that they set up, and it didn't work. And then they also found that the clocks would have to correct for their proportional to their own velocity. Now, what they also, I'm not sure if I have it in the next slide or not, but what Kelly also pointed out is that they're accounting for Earth rotation in the space vehicles, right? So the way that they say it would work out is like it would be satellite velocity plus Earth rotation. Why would a satellite in free fall have to account for Earth rotation in its velocity correction? It doesn't make any sense. So here we have Neil Ashby, the lad that says that the Sagnac effect is in the GPS system as proof of relativity, right? And this is like a giant smokescreen that was put forward after the experiment, the around the world. I'm sorry, not the around the world. That was the Heffel and Keating, the Sagnac effect and global positioning system, right? He went on like a 20-year tour presenting the Sagnac effect as a relativistic, blah, blah, blah. But anyway, so but the important part here is he's defining the free fall of the satellite as a local inertial frame and all that. So, a frame where the speed of light is, where you're going to measure the C being C, you're not going to have a variance proportional to your velocity. But, nevertheless, GPS explicitly functions because of corrections that have to be made of the first order that falsifies special relativity and general relativity. So here we have Carol Alley in 1979 saying, it is appropriate to realize that the first practical application of Einstein's ideas in actual engineering situations with us, the fact that the clocks are now stable and one has to take into small effects to account for the variety of systems undergoing development that are actually compared to time worldwide and are no longer a matter of scientific interest and scientific application, but it has moved to the real realm of engineering and necessity. So this is Carol Alley from the University of Maryland from earlier that we were talking about. And what he's saying here is like, oh, relativity found its way into GPS, and without accounting for these effects that are beyond the order of magnitude of the theory is capable of predicting or producing, somehow it's proof of the theory. Well, let's see what he says in 1995 here. So we have the GPS Relativity and Engineering Overview by the boys over at the GPS Joint Program Office for the government. So we will give an explanation in detail for the formulas for the relativistic corrections to be implemented in high-speed aircraft or in other satellites in connection with GPS or when using GPS from another satellite. Oh, why are you doing that? Aren't they already there? So the OSC of the GPS does not include the rigorous transformation coordinates. Oh, wait, what? It does not include the rigorous transformations between the coordinate systems that Einstein's general relativity theory would require. Transformations to and from the space vehicle and the users on the surface of the rotating Earth are done from the ECI, and they are calculated. Oh, no way. So in the first order timing system. So by the way, that range timing measurement equation, you can actually use that to derive the Sagnac effect. Ruyang Wang showed that in his 2000. I'm not going to quote the year, but maybe like 2004. One of his GPS papers. He shows that how you can derive it for the experiment that this lad did here to account for it directly in the first order. Not Carol Alley. Sorry, I meant Neil Ashby here. And then he also showed it for an interferometer, right? You can do it based off of literally timing. So, yeah. So no relativity required, right? So anyway, however, the new class of user who is going to employ the satellites to obtain the time and space of the space position GPS cannot be satisfied with the current approximations. Therefore, furthermore, because of the approximations, they have not been publicly analyzed, we present a much confusion about the literature, right? So they're saying that basically, in short here, that for everyday Joe use, we don't need relativity theory, and it's just easier to do it this way. But there's going to be a new class of users coming shortly who are going to require precision beyond that which is offered now in the classical sense. So we will eventually move on, right? And then he goes on to give some derivations where he shows that the main reason that they say that they don't correct for these things is because special and general relativity actually cancel each other out. Oh, no way. So they cancel each other out while simultaneously mandatory correct. Like, okay, dude, whatever. But then anyway, we have a follow-up here from the bottom of the paper. We have Carol Alley writing in on the engineering overview here. He says, and if one perhaps does the explicit recognition of the relativistic effects, I mean, it took a long time to get general relativity down properly, and I think this is more or less correct now, but its absence of any explicit acknowledgement of special relativistic effects due to the speed of light being the same whenever measured by an observer, leading to the relativity of simultaneity and the associated Lorentz transformation physics. There's nothing of that modeled in the current system, and I think it should be. Thank you. Oh, no. Snap, dog. So back in the 70s, when it was now no longer a matter of just scientific hypothesis and hypothetical, what could be, it's moved into the realm of engineering necessity. And it's not present. Does anyone want to take bets if they account for it now? Additionally, one has to ensure that the corrections are applied. So this is from, these are the lads that went in to investigate the isotropy of C, right? To find out if old C is C in the way that they say it is, right? Right? Because there's got to be some consequences here somewhere, right? So let me point this out, right? What he's asking here, right? If the principle of relativity of simultaneity is true and cohesive events, that means there can't be a cohesive timeline of events for observers in relative motion, right? So the example they give for lightning striking a train at the end and at the beginning of the train relative to a person at the center of the train, and then also at the same point in time intersected by a stationary observer at the, who's on a platform, saying that the observer that's moving will see the lightning strike at the front first because he's moving towards it, and then the stationary observer will see them both happen at the same time. And this, if we go back to the bomb analogy, we know that it's just a matter of perception. It's not physical reality being actually different for you two. But if that were true, right, those observers on trains and platforms and in different relative motion to one another would all require relativity of simultaneity corrections for their timing to get the distances to be accurate, for them to have an actual position on the graticule, right? For you to be found on the graticule, relative simultaneity would have to be worked out in that respect. And guess what, boys? Nothing. It all just works out. So it turns out you can sync endless events to a cohesive timeline, because that's GPS works, and it's done every day in the face of relativity and Lorentz transformations, the associated Lorentz transformation. So anyway, the lads went to go, investigate the raw data or whatever, the best that they could get to analyze anyway. And the data that they analyzed turned out to already be corrected, and they misappropriated it by calling it a correction for gravitational redshift, right? And then they say, oh, and there's also a second order Doppler shift that they have to account for. And they say it's the so-called Sagnac effect. So these guys, whiffed pretty hard on that. So that's not what's being corrected for at all. It's a first order effect. It's not like an insignificant thing it's literally the thing that they were looking for is that. And they didn't know, I guess, and they just thought it was a second order Doppler shift rate. Doesn't even make sense. So let's see. So that was in the 1990s. So that was Wolf and Pettit who did that. And then we have a review from Daniel Garzi, who's talking about what the Wolf and Pettit lads, like that glaring mistake there. He says, however, Wolf and Pettit noted that Wolf and Pettit, 1997, tested the isotropy of the one-way speed by analyzing GPS satellite network timing signals database and found no dependency on the source to receiver motion, which they interpreted as evidence that C was isotropic. However, Wolf and Pettit noted that the data that they analyzed had been pre-processed and corrected for the Sagnac effect. In this case, the first order timing change of the flight of the radio signal between the satellite to receiver. To justify this correction, they claim that the Sagnac effect was a relativistic effect of the second order in C. Embarrassing. And the correction was therefore a negligible consequence of their analysis. But the corrections that were made were as a first order velocity component to the line of sight of each satellite and to the ground receiver in the ECEF frame. So thus, while the effect of the first order line of sight velocity component of the GPS satellite is clearly evident of the raw timing signal data, the first order component had to be removed from the data set that Wolf and Pettit analyzed to show that C was isotropic. So if you live somewhere that there's a distance discrepancy, and there's just we've got this coordinate system that's like just good enough or whatever, right? Or I'm sorry, they give you this coordinate system and they tell you that this is what it lives on and everything is proportional to this exact coordinate system. What you could do with this is with these corrections, right? These timing corrections, you're essentially adding and removing distances. So you're making it impossible to tell actual distances to anything. You're only going to get distance outputs relative to the graticule in which the GPS system is bound to, based off of the, what it's giving you. And with the corrections, like you're never going to know. It's always going to be graticule. So here we have midnight, noon, and redshift. So this is another big falsification for general relativity here. And this is put forward by Ron Hatch. This argument was actually put forward in the 60s, but that guy whiffed on the math a little bit. And then Neil Ashby stepped in to get to correct that and say that the prediction is like, XYZ amount, super negligible. Maybe we'll get to it. And then Ron Hatch came through and was like, yo, Neil, turns out you're wrong. And it is significant. You would have to correct for it. Here's the numbers. And then, so the story goes that Neil was about to publish his paper, and Ron was publishing the refutation in the same publication. And Neil pulled his paper from it because the editor wouldn't put Ron's on the next month's issue or whatever. Like he wouldn't let it go unrefuted undisputed in the paper. So he took it out of the publication where he was shown that he was wrong. And then now everyone, talks about, like the first Google results will be, Neil Ashby, right? But, your boy couldn't face bronze. But anyway, what the argument is here, to give you an overview, is say we've got some stationary clocks on Earth. We've got a clock facing the sun and we got a clock away from the sun. So midnight and noon. So on noon, you're facing the sun with this clock. Midnight, you're facing away opposite. And there's about, what was it, like 8,000 mile difference between you two, right? So what that means is, the gravitational potential, like the gravitational gradient of the sun, right, is going to be different at the side facing the sun versus the side facing away from the sun. Thus, the midnight, noon redshift, right? So let's introduce the sun's gravitational gradient for effect here. Let's get our production value in, boys. We worked really hard on this. Yep, there we go. Nice,
Wow.
nice. Oh, now we see the gradient, right? So anyway, there's no correction necessary to be made. Like in reality, the dynamics of this don't play out. And they say that, bending and warping, it's causing our velocity that we can't measure, all this stuff, right? But we have to correct for it on the ground at 75 feet. Okay, dog. How about the sun who's dragging everything around, right? At almost 1 billion miles distances, right? I think Saturn's like 800 or 600 million miles away or something like that. So we got this huge gradient here. And we got these really sensitive clocks that retard proportional to gravitational strength. Yet, when they were doing the test in the lab in Harvard, they didn't find that, you know what? The energy shift was actually off because we had to add the Earth's gravitational field plus what the gradient would be over the distance of 93 million miles relative to the sun at our time of day when we're facing the sun, right? Like that would be actual proof that these corrections are like applying to, a solar system and not just like locally, like to our Earth system, right? All this technology is implying is that everything here is close and local, and it's and there's no correspondence to the relationship to why things move in the sky, because gravity should also affect these clocks in the same way to some degree, right? And then we have Ron Hatch
the solar correction, right?
Oh, dude, as well as that, absolutely, totally forgot about that. That is an aspect of it as well, because you're 3 million, dude. Stone, you're the man. Thank you, sir. You're 3 million miles.
One promotion and a raise coming your way, bud.
Yes. So, they should have to correct for that. And there's no change in the density gradient, right? They're no closer to the sun. Like these effects that they say are happening, just do not manifest in any meaningful way. And I was going to play Brian's video out, but I'm having audio sharing issues. So we'll do we'll do a quick recap on Twitter. So I posed a question on Twitter a couple days ago to see if to see what the people on the ground think. Right? Is the Sagnac effect a consequence of general or special relativity, or is it a consequence of, or is it a non-relativistic effect? Right? So we'll see bookmarks, Sagnac. See what kind of responses we got. So we'll start with this lad here. So take a look at the poll results. So we have 51% non-relativistic. Very nice. 28% special.
Are we able to see that window?
Oh, you are. Give me 1 second. I just need to change my screen share. Thank you. Thank you, sir. You see that? Let me make sure it's still of pristine quality.
Yeah, looking good now, man.
There we go. Ooh, no, 720p. Awesome. Disgusting. 1 second. Changing.
No, it looks good.
Nah.
Surprised at 720.
Nah. All right. Now it's at the real ratio. All right. Yeah, so just people putting forward different arguments here, like, oh, well, we'll close on the it was basically just people insulting me a lot, but there was this guy linked a paper to substantiate his claim that it's a consequence of general relativity. So we took a look here at that. What was that paper titled? It was on the general relativistic. Come on, dude. There we go. Your boy Elmo. Shout out to Elmo Wobulation. So anyway, they come here and they hit up your boy, the Landau-Lifshitz metric, right? Which is a which is a tensor that was put forward by the boys. They got together to describe conservation laws on the on that locally rotating scale for the Sagnac effect. So anyway, you can bust this baby on what it is. Anyway, they take it to a cylindrical coordinate system here. And then do you think they length contract it or time dilate it, or do they set up a geometric conveniently position to watch from the center of the device? They watch an observer run around the rim of the device, measuring the speed of light not being the speed of light. What do you think happens?
They finally found Earth orbit motion. They measured it good and hard.
No, they go for the geometrically convenient cylindrical position. The same as, actually, I got to move this into Aether critiques real quick.
Damn, I was thinking, man, maybe they had it.
Yeah, so they ran into the same problem with Tartaglia and Barada, right? So there's no way to explain it as a consequence of relativity with second order effects, unless you just transform to the center of the frame and you just watch it and you just use all the fancy math to describe what it would be like to stand in the center of that rotating device and watch the speed of light not be measured at the speed that it should be. That's literally all they can do. So that was your boy. And then further, I went into some detail on the Landau-Lifshitz metric here. So this is really cool because this is actually a problem originating from Einstein, right? In the original field equations, he had to introduce a pseudo-tensor to satisfy the conservation laws. In other words, he had to interject boundary, where you could define the coordinate system in order for you to have the coordinate system, because it's not dimensionally separated from everything being the energy, the equivalence principle. So with everything being converted into the same thing, you need a separate way to derive a structure to conserve it into, because otherwise it's just not meaningful. So anyway, what he had to do though is introduce the pseudo-tensor, and it gives the appearance of meaningful transformations of invariance under certain ways of doing it. But when you math it out, you can show that it's not dimensionally relevant and it doesn't actually satisfy covariance in any meaningful way. And this issue was known about at the time, and I'll go into there's some citations here I've listed out, but the biggest one is I'm going to be referencing is your boy Levi Civita and what's his name? Something Cabastra. But anyway, these guys invented absolute differential calculus, and what they showed was the solution that the Landau, Lifshitz, and Lavuvu put forward is not valid because they attach Christoph symbols to the tensor itself, and essentially the Christoph symbols describe differential geometry. So they're attaching the coordinate system to the tensor so that they can, they literally do the same thing, and they're like, look, boys, we fixed it. So anyway, Crothers goes through and shows why that's mathematically not consistent. The same thing that the boys did in 1917, the lads who invented absolute differential calculus showed this to be the case. It's a violation of what they call pure mathematics. Like when you analyze it dimensionally, it should be consistent, right? Your coordinate system can't come from not the tensor that it's being derived from. So it's essentially the issue. So it is fancy mathematics, but it's physically meaningless, in other words. So shout out to Crothers for pointing that out. And then let's see if there was one other one. That was, can't even remember. Yeah, it was really nothing. That was kind of nothing. But yeah, just still to this day, not able to derive as a Sagnac effect. So that concludes the presentation. Are there any questions, boys? Questions, comments, concerns?
GPS destroyed in 2 hours. I love it.
Thank you, sir. Yeah, I felt like it was like 200 slides, but it only turned out to be like 72. Pretty decent.
Well, so I think the pattern is we start out with a nice 2 hour girther, as our new buddy Novus will probably explain, right? And then you truncate it to like a 40-minute presentation style. Then you get it to like a 15-minute reel, and then eventually, like we perfected it, we can get it to a 2 to 3 minute blurb, and people will actually.
And then it just
absorb
evolves into a single meme.
And then if we can get it into one meme, it absolutely will take off.
Indeed.
All of relativity and GPS and Sagnac. Yeah, one meme. I'll work on it.
Yep. So let's see. Yeah, man. Sagnac can't be a consequence of relativity theory.
I like how they keep encountering the same problem, but calling it something different. They keep having to fight this battle over and over again, like they're winning this giant facade, and it's like, nah, you retards, you just keep doing the same thing over and over again, and the first guy doesn't tell the next guy what's happening. It's like a big Larry Curly marathon going on, right? And then you get like people who work in the industry who just like do what they're told, who make this meridian / Sagnac / velocity correction or whatever your group calls it, right? And then you never know what you're actually correcting for, and it's called many different things, and it's always the same correction, always accounting for ether, right?
Always.
Oh, people are like, what technology is ether? It's like, oh, bro, you never heard of GPS? Yeah, not possible. Direct evidence of ether has to account for it directly all the time. Hence, coordinate systems and the invention of an ECI frame in which to do it right under your nose. So that today, people like you will just say GPS proofs, the Earth rotates around the sun, and we're like, no, opposite of that. Like in every way, opposite.
Dude, exact opposite. Because you know what it would prove too, right? At the very least, it would prove that the gravitational influence relative to the time of year, like Stone was saying, is present, right? Suppose the velocity, you can't do it. If the relativity is true, it can't be done. But the gravitational influence would definitely be there, right? You would definitely measure a fluctuation corresponding to the time of year with atomic clocks like that. And it would be at a ratio of the mass of the
It's actually a second level of complexity there too. I mean, you were looking at the final image there, where it was the midnight versus noon at one rotational point, one revolutional point around the sun. Well, that's going to establish a particular gradient at 94.1 million miles away from the sun. But once we come down to 91.5 million miles from the sun, that gradient between midnight and noon is actually also different.
Yeah.
If you can catch that proportionality because of
it's constantly going to be in flux. They would have to have like done it for like a couple of years, established the fluctuation rates, and then mapped it cyclically.
It's a 6-month sliding ratio.
Yeah, exactly. There's nothing, guys, nothing.
That was excellent, Alan. I think that none of the Globers are going to watch it, and like we're going to have to work on distilling it to a digest. So like, because like it's hard to argue GPS with Globers because you have to explain all the prerequisite knowledge and background to get like it's like, oh, I destroyed you. Oh, but you're too dumb to understand how and why. Okay, I gotta go through some stuff, you know. Like,
so prior to the equigravitational potential correction, I would agree that you could only use GPS as an argument for motion, but yeah, it just body bagged reciprocal zennies and deflection of the vertical.
Yeah, which are all just hidden under guises for astronomical celestial geodesic conversion or whatever, right? Like as they state openly.
Yeah.
But yeah, we want to get those two together as close as we can.
But yeah, like now I'll more confidently do, or, you know, make it a flat earth argument because that's, you know, easy peas. If your explanation is Earth oblate rotate through stationary gravitational field, great. Mine is two equipotential planes.
And it's like now you get in trouble because all that geopotential, the equigeopotential that we had to align to based on the geoid because of the directionality, that makes sense now, right? And it's like it's their catch-all. You remember the song "Wake Up on the Wrong Side of the Sleep" geoid or whatever? And it's like, yeah, if you don't do that, well, you're wrong. That's so right today, though. Like if you don't do that, none of your reference framework satellites won't work. Without that, like the whole thing would fall apart. So.
Beautifully said.
Yeah, it's fantastic, Alan.
Thank you, sir.
It's crazy because it's like I think back to like a year or two ago, arguing with people about relativity and not really knowing what I was talking about very much, but I just knew it was wrong, like because I knew like the craziness of it, like the twin paradox and all these crazy paradoxes inherent with it, and then like. Bennett came along and gave those presentations on what's it called on Witz's show.
Yeah,
went live and gave a presentation there.
Game changer.
The psi prop analysis. Yeah, and like there were so many, which you kind of went over here tonight with Fresnel, Drag, and then with Dufour and Prunier. It's like it's such a like that was one of their get out of jail free cards was the not being in that frame. And then Dufour and Prunier, like they did that back in the mid 1900s.
Smoked them. They've been smoked forever.
Them. And I never heard about it until like within a year, like within the last year of my life.
Crazy.
And I've always been told that relativity is real and, it's all, and yet, there it is back in the mid 1900s, they annihilated one of the main precepts of the whole thing.
Yeah, right off the rip, dog. Right off the rip.
You imagine they could just take something like that and just literally sweep it under the rug and don't talk about it. Like, hey, let's just play. We'll never mention that. It's like a kid cleaning their room. They shoved all this shit in the closet and then they just didn't tell anyone. Right? That's the relationship to what they're doing. Oh, did that disprove us? No, it didn't. What do you mean? Yeah, I'm just gonna say no.
But with so much mathematics on the table, it has to be real.
Dude, that's where they get you, dog. That's where my boy Steven Crothers came in hot and started analyzing the tensor situation because he was actually going to get his PhD in doing a mathematical analysis on the validity of general relativity. And once he realized that it wasn't, what is that? Oh, Mister, thank you, sir. Once he realized it wasn't dimensionally consistent, he was like, yo, boys, this is actually full DS. And then, let's see. Yeah. So he presented it to his PhD candidature sponsor, and that guy had to drop him. Right. The faculty, like they were not going to let that go through and let him graduate on falsifying general relativity. Right. So it got to the point where instead of critiquing his math, right, because I can't do the math to verify what he's saying, right, but there's allegedly a bunch of smart lads that can do this math. And how they treated him and what they did to him in response to his math did not refute it at all. So I take what he did with his math as solid, because what they did was the first guy at the faculty that he was getting his PhD in these disputes ended up having to go to a board review. And anyway, the guy that he submitted his work to and made the critique to take him off the candidature, changed his work, changed what was submitted, and then made critiques based off of the changes that he made as to why it was invalid. And Crothers was like, "What? You can't do that, dog. That doesn't make any what are you doing, bro?" And that was never addressed. Nobody ever punished him for that at the because after the hearing and all that, because it got crazy. But anyway, that was never addressed. Nothing ever came out of that. And then he gets into an argument with the International Gravitational and Relativity or General Relativity Committee, right? So these guys set the standard for how to interpret the equations mathematically, because they're nonlinear field equations. So when you set them, you have to rein them in and make approximations to get answers out of them. So these guys set the interpretation of what you're allowed to do, so to speak, to get the bending and the warping of the space and the time. And this guy, the head of the organization at the time, was Crothers presents his work to him, and that guy did the same thing, bro, and then even says, he was like, people figure this out from time to time and make a big deal about it, and they think that they're smarter than Einstein. You're not special. That was that was literally his answer to it. It was like, what? Sometimes people find out general covariance is fake.
Doesn't mean it does. All we do is we don't acknowledge it and it goes away. Peon, you don't threaten us,
dude. Yeah. So when I seen that response from the heads of these people, I'll stand on Crothers' work all day and try and understand it the best I can to articulate what it's doing to the math, because that dude apparently nailed it so hard that not a single relativist has ever refuted him mathematically. And he's been doing presentations for 10, 15 years now.
And these people have no idea, right? They assume that in the scientific community, if you're right and you present math, the whole world will just cave and bow to you. Obviously, it's all about being right and the secret of truth in the scientific community of academia, right? So, of course, if that were the case, Alan, everybody would know it.
Right.
Therefore, you can't be, therefore you're wrong. So stupid.
Therefore, I definitely
thoroughly enjoyed Crothers. I thought he was great. I knew I was in for a good ride when the first thing that he did was debate the dimensionality aspect of the term space-time. It's like, right. Dude, it's an A-ticket ride.
Straight savage, bro. He is so smart. You can just tell by his disgust of it. But what he gets, he writes a lot of insults and stuff as he's writing it, but it's he's disgusted. It's not anyway, it's funny.
It's one pissed off Kiwi.
Yeah, he's just so mad. He's triggered Toby, dude. He's like, why won't anyone address this math? Everyone wants to sit around and pretend that C is C or what have you. And they actually, I don't ever think I've heard him make any specific claims about that, but he gets it. So anyway, if there's no further questions or anything like that.
You know what they did? They went, oh, you know what? You're right at him. They pulled the wits it. They were
dude, they wits it.
You know what? You know what? You're right. Sit down, cut it. God damn it.
That's what happened. So, Mister, if you got your guitar ready, dog, I heard you strumming them strings. If you want to play us out, if not, I'll come up with a way to play that audio for us. Cause I heard that riff you did a couple Flat Earth Fridays ago, and it was awesome.
Sorry. I heard noise immediately.
Sorry, go ahead.
Before you do, can I have a quick question, Alan?
Yeah, absolutely.
So as I gathered, the classic theories can fully predict the friendships with the Sagnac. I heard you say, to be consistent with relativity, the Sagnac interferometer and ring laser can't lead to a fringe if the equipment's in uniform motion. In their paradigm, they don't have an explanation for that. Am I to understand to this day that this is still a showstopper and they don't have any apologetics for that?
Full showstopper, bro. The most recent papers in 2022 by Barreda and others analyzing the Ruyong-Wong experiment, right? Forget about the regular rotating circle path that clearly applies to this dude. They're trying to do it for Wang. and they can't do it either. They can only do it through the thought experiment of setting up for your geometrically convenient position, right? And then just chilling. Just sitting there watching, right? Just watch as you're in the center frame, in the relative motion frames over here, and C is supposed to be C for you, right? And C is supposed to be C for this lad. You're over here watching this guy, and C's not C, C's not C, C's not C, C's not C, C, and you're just like, no, relative, why? Can somebody help?
I recommend you take them out of the knees right in the door. Just attack their paradoxical nomenclature, like curvilinear.
Yeah.
Just start there, man. They have nothing to stand on after you take them down at that level.
It's facts, man.
What surprised me is that Alan mentioning the summation of the Lorentz transformation equations gets you right back to the lab frame. So that's interesting. I gotta look into that math more.
It's like the math trail of how to get out of the lab frame. It's like, oh, you did it right, but we see the trail, and here we are right back.
Dude, how about that? That's so cool. Yeah, dude, that guy, that was from Consoli Mazzario or Mazzario or something like that. The guy that did that in-depth analysis, the harmonic analysis on the interference fringes.
Yeah, I got the screenshots.
Oh yeah. He did that. So I'll send you his paper. It's badass. The dude's a legend. It's like 90 pages or something, or 60 pages. I haven't read it all, but like just the 14 or 16 or so that I read was just insane. He was just dropping all kinds of sauce.
Awesome, man. I learned a lot from this one. Great show, boss.
Thank you.
Cool, yeah. So check us out for Thursday night discussions, Monday night reading, and Tuesday night roundtables. And then if there are no further questions, maybe we got some tunes. Is that what I hear?
Yes, sir. I think Mister is going to play us out.
Yeah, so last night after listening, that's crazy that you said that, because last night watching Cassandra's stuff and listening to all that awful music, by the time I was done listening to the whole thing, I had written this, and I think it's a little more appropriate for what you guys got going on. So we're going to try it. If it sounds like shit, we're going to hope not, but feel free to mute me if it does.
That's the risk we take as performers. Go for it.
One Monday night, Cassandra brought the juice. Ether cause, calling out the truth. Kinematic, dynamic in style. Hide your wives and your daughters. These boys are on fire. Hildegard, model after God. Hildegard, Einstein was wrong. Hildegard, model after God. Hildegard, Shane, here's your lats, and Shane, here's your lats, and long. Reading night, at a party if you're cool. Ether cause, calling out the fool. Space audits is always on point. Step up to test them. These boys will smoke you like a joint. Hildegard, modeled after God. Hildegard, Einstein was wrong. Hildegard, modeled after God. Hildegard, Shane, here's your lats, and Shane, here's your lats, and long. There you go, boys.
That was awesome. Thank
Wow.
That was amazing,
Nice.
dude. Thank you.
That was fantastic,
amazing.
bro.
Well,
That was
hopefully
awesome.
that sounded all right.
Honestly, you were shitting through the microphone. You have to record that so we can play it as like an outro. You know?
No, that was fantastic.
Yeah.
Thank you for doing that. We
It was-
appreciate it.
It was
And for
awesome.
everyone listening at home, thank you for listening in and take good care of yourselves. Good night. Or I guess you don't have to be listening at home. You could be on Camelback.
Hey, thank you so much for this. And I want to apologize to Toby and Shane and Alan for disturbing you guys during this presentation. I have no idea what happened, but it finally worked and I got connected. So sorry and thank you.
No, all good. You can ping me again. We did change the security setting this morning, so I don't know if it was related to that or not. So I may change that back. And if so, and you run into the problem again, don't hesitate to ping us. But I'll let you know if I change it back.
Yeah, it probably was related to that because I did everything as normal and it just it took me all the way to, I got the invite and then I pushed the invite and then it says join the chat voice. And then when I pushed that, it said I didn't have permission. So yeah, it's very weird. So thank you so much for your patience. God bless you guys. You guys are so patient with me. Thank you.
Oh, no problem. No problem at all. Not a big deal.
We couldn't figure it out. Do you know why she can't get in? Nope. Do you know why? Nope. At first, I made her mod, and I was like, "Oh, that didn't fix it." I don't know, Toby. Like, making her mod doesn't do it. I'm out. I don't know how to.
All right, I'm back. Sorry about that. I had to go AFK.
Oh, no, fuck, I would do it.
Mister, that was awesome, Mister. Thanks for
Oh,
playing.
I missed it, dude. Oh, are you fucking kidding me?
Dude, I did not expect. Wait, is your stream still going?
Yeah.
Oh yeah, I closed mine out already.
Oh no, I had an
Everybody.
emergency. I had an emergency. I was AFK. I just got back.
Well, I already closed out for him, but
Encore?
Yeah, it's on there.
Encore, dog,
the
or
true
what?
fans are still here.
Dude, God, dang it. Well, thanks for playing, man. I appreciate that.
I don't know how it sounds to the phone, dude. Honestly, like
I'm sure it's
not
fine.
someone said that it sounded like someone said it sounded like shit, but
Well, I mean, it was great. I could hear enough to hear that it was awesome and that I loved it.
Shit. All right.
I do
well,
need
I'll be
to
right
get
back. I'm gonna
like
close
all
out.
this.
All right, lads. Thanks for coming out to the show. I hope everyone enjoyed. I saw that I got some super chats earlier. Thank you very much. Much appreciated. We are funded by the people. And make sure you check out brushtail.coffee for Toby's penguin-free coffee. And catch us later in the week, boys. We'll be back on Thursday.